needs to remember to hit record. Sorry about that. We just we're gonna have missed the first half hour. Okay, we're recording now. Sorry about that. Back to what I was saying. The first real rule: the slope of the shear diagram at any point is equal to the magnitude of the load at that point. And some of this won't make any sense until I draw some pictures, but go with me till we get all through 4 of these. But the first one is the slope of the shear diagram at any point on the span is equal to the magnitude of the load on the span at that same point. And the mathematical equivalence of that is dV dx is the slope of the shear diagram is equal to the magnitude of the loading diagram. Number B, the slope of the moment diagram at any point on a span is equal to the magnitude of the shear at that point. So dm dx is the change in moment over change in x span. So the slope of the moment diagram is equal to the magnitude of the shear diagram. C, the change in shear between any 2 points is equal to the area of the load diagram between the same points. So we're going to say that dV is the change in shear is equal to the area of the load diagram between the 2 points. The change in moment between any 2 points is equal to the area of the shear diagram between the same points. So dm is equal to v dx. And of course, anytime you see the area, that means we're going to get into some integrals. So the moment is equal to the integral of the shear diagram, or the change in the slope of the shear diagram, and the shear is equal to the integral of the slope of the load diagram.
Sorry, Professor, can you go back to the previous slide?
Okay, let me know when you're ready.
Okay, you're good. Thank you so much.
Okay. Okay, so this sets up some ground rules here, where if I have a point load, as indicated by this arrow here, just a singular load at a point, then that means the shear is going to be constant and the moment is going to be linear. If I have a uniform load, then the shear is going to be linear. The moment is going to be parabolic. See how each one of these works? So the shear is the integral of the load, and the moment is the integral of the shear. So each one of these is increasing. This one's constant, a function of x, a function of x squared. If I have a linear load, where the load is a function of x, then the shear is going to be parabolic. The moment will be cubic. And if I had, for some strange reason, a parabolic load situation, then the shear would be cubic and the moment would be quartic. Yes, I actually had to look that word up. Okay, so remember example number 1, where we had a 25-foot span and simply supported beam, 3 kips per lineal foot. So we still need to create a free body diagram, and we still need to solve for our reactions. That's still always the first step. Find your reactions. The resultant of the uniform load is 3 kips per lineal foot times 25 feet, gives me 75 kips. So to find my reactions, I sum my moments about A. I'm going to go through this a little quicker because it's the same as we just did last lecture. And reaction at B is 37.5 kips up. Sum the forces in the vertical direction. I have minus 75 plus my reaction at A plus 37.5 equals 0. Therefore, my reaction at A is 37.5 kips up. So now we draw all the forces and reactions on a free body diagram, create a load diagram. So here is my free body diagram or load diagram. Again, as I said, the resultant is only good for finding your reactions. Go back to the real loading at this step here. So just repeating the same diagram here, start drawing the shear diagram. Start at the left-hand side and the change in the shear diagram is equal to the area of the load diagram. The change in shear is equal to the area of load between any 2 points. So the change in the shear is equal to the load. The load goes straight up 37.5, so the shear diagram goes straight up 37.5. Now, between points A and B, what is the change in the shear diagram equal to?
The area of the loading diagram.
Thank you. The change in shear between any 2 points is equal to the area of the load diagram between the same points. Okay, have that in your mind? Okay, we were right here. So the change in the shear diagram from A to B is equal to somebody? Almost, Mustafa, very close. But say the words. The change in the shear diagram from A to B is equal to
The area of the load.
The area of the load diagram from A to B. That is right. Okay, so this load diagram, remember at the beginning of the last lecture, I told you that this is actually pushing down this load. I didn't draw it with all the pretty arrows at this point, but this load is pushing down. So that means that this load is actually minus 3 kips. The magnitude of this load diagram is minus 3 kips per lineal foot. And the area from A to B, this is 25 feet. So the area of the load diagram is minus 3 times 25 is equal to minus 75 kips. So the change in the shear diagram from A to B is equal to minus 75 kips, which looks like this. So 37.5 minus 75 kips is minus 37.5 kips. That's the shear diagram right here. And then we're not done. What's the last thing that happens? The load goes up 37.5. So the shear diagram goes up 37.5 to return us back to 0. Okay? You always have to end up back where you started. We started at 0, you end up at 0. Okay? Any questions on the shear?
How do you find where it crosses 0, like laterally using the graphical method?
You would use similar triangles. And that's a good question. So you would want to use similar triangles, in which case it's almost obvious that's right at midspan. But if this is a more complicated shape where you cannot use similar triangles, then you can always resort back to making a cut and finding the equation. Okay, what about the moment diagram? Well, it helps to know where do you start for a moment diagram at the left-hand end of the beam where there are no applied moments and there's no restraint of moment. So where does the moment diagram have to start?
0.
At 0. So we start at 0. Now, I know this is going to be agonizing, but I have to say it a lot of times before it sinks in. The change in the moment diagram is equal to the area of the shear diagram between the same points. So the change in the moment diagram is equal to the area of the shear diagram. So how do I know where the maximum moment is?
When x equals 0 at the shear, like when I mean in the intersection point.
Yes, when the shear is equal to 0 at the inflection point, that is your maximum moment. Now here's the reason why that's maximum moment. Say like I think the maximum moment is right here. So the area of the change in the moment is equal to the area of the shear diagram. So this means that the moment grew by this much area. Well, this can't be the maximum because it's going to grow some more over here. I got more shear that would cause it to grow even more. But if I look over here someplace, then I've got all this positive shear minus some of this negative shear. So this can't be the maximum because it's going to drop somewhat. So it has to be right here where you have collected all the positive shear, but you haven't started going back down yet. So how do I, using the geometric method, how do I find the magnitude of the maximum moment?
The change in moment would be the area of the 37.5 kip triangle in the shear diagram.
Exactly. That is perfect. So right there, the change in the moment is equal to the area of the shear. So the change in the moment would be equal to 37.5 times 12.5 feet times half. That's this area. Looks kind of like that. Change in the moment is equal to the area of the shear diagram. So 37.5 is the height times 12.5 is the width times 1/2 because it's a triangle. My maximum moment is 234.4 kip feet. Now, that's only half of the moment diagram. What happens on the other half of the moment diagram.
It should be symmetric.
I'm sorry, say again?
It should be symmetric, right?
It
Right.
should be,
Like because it's the shear is symmetric, so it's gonna like go to zero. Same.
okay. Yes,
Completely.
it is symmetric, but it's also this, all of this shear here, I'll highlight this this way. This whole area is negative. That's minus 37.5. So negative shear brings the moment diagram back down. So the change in the moment diagram is the equal to this area, which is going to be minus 234.4 kip feet. So that means it's going to go from 234.4 kip feet to 234.4 minus 234.4, which brings you back to 0. Like so. And this is your check. You should always make sure that you got back to 0. If you do not get back to 0, then you have made a mistake someplace. Okay, so this is exactly what I do here. I go from this point is 234.4 to this point is 234.4 minus 37.5 times 12 and a half times a half, and that does in fact equal 0. Okay, so we got the same result as we did by using the equations, but we did it with presumably a lot less work. But again, I'm going to keep hammering on the principle. The principle is that to find the moment at any given point, you have to start from somewhere. Because remember, we're only talking about the change in the moment diagram. This is not absolute. It's a change in moment diagram. But we started from 0. So any positive shear starting from 0 gets you to the maximum. The change in moment from the center to the other end is equal to minus 234.4. But we started at 234.4. Minus 234.4 got us back to 0. You could find the moment anywhere on this by using the same principle. I'm not going to go through the math of it, but just for example, say you wanted the moment right here. Well, then you would look at the change in moment from here to here is equal to the area of the shear diagram between the same points. So you could figure out the area of this shear diagram, and that would tell you from 0 how much the moment diagram has grown. Okay. By the same token, you could also say, I want to know what is the change in the moment diagram from this point to this point. How much does the moment diagram change from here to here? Well, the change in the moment diagram from here to here is equal to the area of the shear diagram from the same 2 points. What is the area of the shear diagram from A to B? It is 0. That's right, because all this positive is canceled by all this negative. Exactly. So the area, the total area of the shear diagram from A to B is equal to 0. So the moment, the change in moment from A to B is 0. Okay, guys seeing how this works? Okay, let's go to our next example. Oh, before I do, one other point. Forgot about this. Okay, the slope of the moment diagram is equal to the magnitude of the shear diagram at that point. Okay, you can see they're intimately related. The differential, one is the magnitude of the other. The integral, the one is the magnitude of the other. They're related by integration differentiation. So this slope here is equal to the magnitude of the shear diagram at the same point. The magnitude of the shear diagram here is fairly large, so the slope of the moment diagram from 0 is fairly large. The slope of the moment diagram at this point is equal to the magnitude of the shear diagram, which is 0. So at midspan, shear is equal to 0, so the slope has to be equal to 0. That's another confirmation that your maximum on the moment diagram is where the shear is equal to 0. Okay, example number 2. Remember our old friend? The beam from A to B with an 8 kip point load at 10 feet. We need to find our reactions first, always the first step. So I have an unknown A, unknown B. Find my reactions, sum my moments, 8 times 10 minus reaction at B times 25. My reaction at B is 3.2 kips up. Sum the forces in the vertical. My reaction at A is 4.8 kips up, right? So far, this is exactly the same as we did last lecture. But let's, okay, we draw our load diagram. Here's everything on here. But now we don't ask how many cuts do we need. See, we're shortcutting that part of it. We can make this a little simpler. We're just going to start drawing the shear diagram. So if I start at the left-hand side, what's the first thing that the load diagram does? The very first thing.
4.8.
It goes straight up 4.8. So my shear diagram goes straight up 4.8. Okay. Now, and I know this gets repetitive, but the change in the shear diagram is equal to the area of the load diagram. So what is the area of the load diagram between these 2 points? It's
0.
It's a constant 0, that's right. The area of the load diagram between the reaction and the point load is 0. There is no load between these 2 points. So how much does the shear change?
It will be constant, go until the second force.
Okay, so for everybody's sake, the change of the shear diagram is equal to the area of the load diagram. The area of the load diagram is 0, so the change in shear is 0. The shear remains constant. There is no change until we get to the 8 kips. Now, what is the change in the load diagram? It is minus 8 kips. So the shear diagram goes down minus 8 kips. Now, it does not go to minus 8 kips. It's relative. Remember the definition. The change in shear is equal to the magnitude of the load. So it was at 4.8, it goes down 8 kips to minus 3.2 kips. Okay, now the same question. What is the area of the load diagram in this region? The area is equal to 0. So the change in shear is equal to 0. It stays constant. But we're not done. What's the last thing that the load diagram does? It goes back up 3.2. So we go up 3.2, and you had better get back to 0 or there's a mistake someplace. Okay, so look what we just did. We just talked our way through the shear diagram without any cuts at all. How about the moment diagram? If I do not have an end moment and I do not have any end restraint, where does the moment diagram have to start?
On 0.
We start at 0. So we start at 0, but the change in the moment diagram is equal to the area of the shear diagram. So this thing is going, this is positive shear, so the moment diagram is going to go up. The area of this is 4.8. I think this was 10 feet. So we're going to go up 4.8 times 10 feet is 48 kip feet. So here, again, the change in moment is equal to the area of the shear. How do I know it's a straight line? Because this is constant, so this is linear. Go back to the slide that I gave you. A point load creates a constant shear, creates a linear moment. That's how you know. Now, that gets me to this point. How do I get back down to here? Well, the change in moment is equal to the area of the shear. The area of the shear is minus 3.2 times, I think that was, what was that, 20? Shoot, I forgot.
It's 25 minutes 10, I think. Yeah.
Yeah, so it's 15. Okay, sorry about that. So minus 3.2 times 15 is equal to minus 48. So the change in moment is equal to the area of the shear. So it goes from 48 minus 48, and you had better get back to 0. Okay, there it is, the shear moment diagrams. Any questions on example number 2? Okay, example number 3. Here is our friend with the applied moment. So this might throw us for a loop a little bit. What's my first step?
Find the reaction.
Find our reactions. Okay, so we're going to create a free body diagram. You know, I just realized something. There are 24 of you here, and I think I've got 32 in this class. And I forgot to hit record for the first about 20, 30 minutes of this class. Just making a point. You never know when the recording's not going to work. So good thing you guys are all here for the class. Just an observation. Okay, create a free body diagram. Find our reactions. This is the same as last lecture. 600 kip feet positive minus RBY times 30. That gives me 20 kips up. And sum my forces. And the only vertical I have is the 20 kips up. So A is 20 kips down. And here's my loading diagram. Okay, so I got 20 kips down, 600 kip feet, applied moment, 20 kips up. Okay, so we start drawing our shear diagram. What is the very first thing that the load diagram does?
Start from negative 20.
First thing the load diagram is goes down 20, so our shear diagram is going to go down 20. And again, why? What the theory is? Why? The change in shear is equal to the area of the loading. So the area of the loading at this one discrete point is 20 kips. So the change in shear is 20 kips. Now, between the 20 kips and the applied moment, what's the applied load?
0.
equal to 0. So the shear is constant. I kind of jumped ahead a little bit here. What is the change in load here at the 600 kip feet? There is no change in the vertical load. There is no vertical load on the loading diagram. So the shear doesn't change. And likewise, from here all the way to the end, there's still no change in the load diagram. So the shear diagram does not change. And then we get to the end and the load diagram goes up 20. So we go up 20 to get us back to 0. Okay, so a applied moment has no effect on the shear diagram. That's the interesting part about this. Moment diagram. I start at 0 because there's no end moment and there's no fixity at the end. So I start at 0. The change in the moment diagram is equal to the area of the shear diagram. So we are actually looking for, let me draw a little divisor here. We're looking for the change in moment from the end to this line. And the change in moment from the end to this line is equal to the area of the shear diagram here, from this point to this point. Yep. So this is constant. So the moment is going to be linear. And it is going to be minus 20 times 12 feet is minus 240. So this goes down linearly to minus 240. Then what happens? The change in the moment is equal to this change here. This is an applied moment, and it's a positive 600 kip feet. So the moment diagram goes up positive 600 kip feet. So minus 240 plus 600 gives me to 360 at this point. And then the change in the moment from this point is equal to the area of the shear, which would then be 360 minus the 20 times 18 feet brings me back to 0, like so. Okay, so an applied moment makes a jump in the moment diagram. An applied point load makes a jump in the shear diagram. Does that make sense? And always make sure that you start from 0, end at 0, start from 0, end at 0, unless you have some kind of an end reaction. An applied moment at the end or a restraint of the moment at the end, then that's different. Okay, any questions about example number 3? Okay, here's example number 4. And this one might be a little different. First thing we do, find our reactions. So I draw my free body diagram. I put my applied loading on it. I put my unknown reactions on it. Just like we did last time, we solve for our reaction. My moment is minus 450. So that means my reaction is counterclockwise. Sum for the vertical reactions. And I find that my vertical reaction at A is 50 kips up. So now we draw the diagram with all of our applied loading and all of our reactions on it with the correct arrows. Okay, so now we can start drawing our shear diagram. Start at the left-hand side. What is the very first thing that happens to the shear diagram? we go up 50, just like that. Now, what do we do about this 450 on the shear diagram?
It doesn't matter because it's like moment. It's not affecting the shear.
That is
Diagram.
correct. That is correct. This is an applied moment. It does not affect the shear diagram. So we do nothing. What other loads do we have between the left end and the right end? What other applied loading do we have? Anybody?
It should be constant until like reach the end of the second load, which is -50.
That is correct. So I'm trying to draw you all out. I want to make sure that everybody is understanding this. And fantastic that a handful of you are getting this. This is great. I don't know if you're all getting this or not, or if there are some of you that are quiet and just completely lost. I don't know because I can't see you all. But for those of you who are getting it, fantastic. And I apologize if this is dragging, but I want to make sure that nobody's being left behind here. If you feel like you are, please speak up or hit me up on the office hour. Well, you know, whatever you're comfortable with, but it's important that we're getting this. Okay. Thank you, Natalie. Okay, so and again, drag this out, but the change in shear is equal to the area of the load. There is no load between these 2 points, so there is no change in shear. That makes the shear constant. Then we get to the very end, the change in the load is down 50, so the shear goes down 50, and we end up at 0. Okay, that's how we know we've completed that loop. Now the moment diagram. Okay, now here's the trick. What is the very first thing that the loading diagram does with respect to moment?
Starts at a negative 450 kip feet.
It starts at, let me rephrase that just slightly. You're right, but it starts at 450 kip feet. But is that 450 positive or negative?
Positive.
It is counterclockwise. It is negative. So we go down 450. Why do we go down? Because this is negative. It's counterclockwise.
Is that what you're like your assumption, or is that just a definite I forgot the word to describe the different positive and negative
No, yeah, it's like a sign convention.
orientation.
Or,
Yeah.
okay. No, it's defined. It's not assumed. It's defined. But here's how you would know if you did it right or wrong. Because it is confusing. Sure, I'm looking at it. It could be confusing. I'm saying it's negative because it's counterclockwise to our sign convention, but that could be easily very easy to get the wrong sign on that. Here's how you know if you did it right or not. The shear, we all agree, and there's very little controversy, that the shear is positive through the whole span. The reaction was up, so the shear is up. The shear is positive the whole time. If I had assumed that the moment was positive, and then the change in moment is equal to the shear, I would have got this moment that grew to be very large. And then at the end here, I would have put another 300 kip feet on it and made it even bigger. And it would not have closed the loop. So that's how you know that that was the wrong assumption. Now, if you do it correctly, counterclockwise, negative moment, so this is minus 450, and then the change in moment is equal to the shear. So then you go up because the shear is positive, and this is 50 times 15 feet. So minus 450 plus 50 times 15 feet gets you to a positive 300. And then this 300 here is counterclockwise. It's negative. So then you go back down and you end up at 0. So that's how you know this is correct. You started at 0, you ended at 0. Even with these end restraint and end moment, you still close the loop. It all closed back to 0. If you had made the assumption, and easy to do, I'm not faulting anybody for, forgetting or making the opposite assumption. But here's what would have happened. You would have gone up 450. Then you would have said, the professor said 1,500 different times that the change in the moment is equal to the area of the shear. So the area of the shear is 50 times 15. That's 750. So I go up 750. And then if this was positive, then this is positive. So then I go up 300. And where am I now? I'm at 450 plus 750 is 1,200 plus 300. I'm at 1,500 kip feet, not 0. So you would know that this is totally, I can't do it that. That would tell you that this is totally bogus.
Wait, Professor, I have a question.
Great.
So when you in the beginning, when you started finding your reactions, you claimed that counterclockwise was negative, right? And then clockwise is positive.
Yes.
So let's say if I want to do it the opposite way, but I'm consistent throughout the whole thing, I'll get, like I say, counterclockwise is positive and clockwise is negative. We'll still get the same answer, right? If you're consistent throughout the whole problem, or no?
Okay, good question. Let me work through it. Let me see what would happen. My gut is telling me no. But let's take a look and see. Okay, so you would get here, and if you assume that clockwise is negative, then you would have had positive 300 minus positive, you still would have gotten minus 450 here. So you still would have had counterclockwise as the reaction. So you would have gotten to here with all the same numbers. Yeah, okay. So you would have got, Raphael, you're still there? You would have gotten to this point and you would have had all the same numbers and the same direction.
Okay.
Okay?
Yeah.
So it doesn't matter what you assumed here, clockwise or counterclockwise, you would have ended up with this diagram either way. So now we got that diagram. Now we move down here. And that's, okay, so now you're at the point where if this was your definition of positive, you would have gone up, 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 and been utterly destroyed. Okay, did that answer your question?
Yeah, I did.
Okay. Let me get to the bottom of this slide here. Again, Whether or not you call this positive or negative, at some point, it is no longer arbitrary at all. At some point, there is a definite right answer and a definitely wrong answer. And if you get to the moment diagram, and let me just do this. I know we're almost out of time, but if you drew the moment diagram like this, and you said this is 450 and this is minus 300, that is not arbitrary. That is not to your whim of which way you want to look at it. If you say this is 400, that is dead flat wrong. It is absolutely wrong. If you said this is minus 300, that is wrong. 300 and minus 300 mean completely different things to the beam. It means that your stresses, when we get to finding stresses, you'll have the wrong stress in the wrong place. So that we've gone from, okay, you can go counterclockwise or you can go clockwise. It doesn't matter. Everybody's going to get the same answer, to now we have gone beyond statics to a point where, okay, everybody, it's not arbitrary anymore. You got to follow my rules or you're going to get the wrong answer. I know that sounds bad, but that's what it is.
Professor, I have a question real quick.
Sure.
So you see the red diagram that you drew for the moments, like the triangles, the first one being up and then the second one being down. So
Yes.
is that would be the answer if and only if the shear diagram here was negative, right?
That's right.
Okay,
Yes.
yeah. All right, I understand it then.
Okay, great. Sorry, guys, we ran out of time. So we finished example 4 again. So we're going to start with example 5 on Tuesday, and we'll go forward from there. We're out of time. So everybody have a great weekend. Don't forget to look for homework number 9, and we will see you on Tuesday. Thank you.
Thank you, Professor.
Thank you.
Thank you, Professor.